Okay, so today we're going to do two sections. Chapter 11, Section 1, space of figures, three-dimensional figures, and cross-sections, and then 11.2, which is prisms and cylinder, surface area and lateral area. All right, so a lot of definitions. The first definition they give us is that of a polyhedron. And here the book says that the polyhedron is a space figure or three-dimensional shape whose surface areas are polygon. Each polygon is a face of a polyhedron, and an edge is a segment that is formed by an intersection of two faces, and a vertex is a point where three or more edges intersect. Okay, polyhedron. Polyhedron is a three-dimensional figure, and it's a three-dimensional figure such that the faces or the sides of the three-dimensional figure is a polygon. Remember, we talked about polygons being shapes such as triangles, squares, uh, quadrilaterals, squares, rectangles, etc., rhombus, kites, uh, or pentagons, hexagons, octagons, nonagons, decagons. Anything where it has a particular side, right? These guys are called polyhedrons. Uh, the face is one of the polygons of the polyhedron. So in this case, we have for this rectangular prism, because the faces are rectangles or the sides are rectangles, so we call this a rectangular prism. The faces would be any shape, any two-dimensional shape. So in this case, all the two-dimensional shapes are rectangles. So we have a rectangle on top, a rectangle on bottom. Those are two faces. We have a rectangle to the left. We have a rectangle to the right. Those are two other faces. We have a rectangle in the front and a rectangle in the back. So this particular polyhedron or rectangular prism has six faces because it has six sides. And then we have something called the edges. And the edges are the places where two faces meet. So if I look at the front face and the face to the right, they meet right here and this edge, and they form edges. So this particular face has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think 12 edges, I believe. I'm probably wrong, but I don't feel like counting all those edges. And then we have vertices, or the vertex. And that's where three or more edges meet. So basically the corners. So this particular polyhedron has less vertices, so I can count that. 1, 2, 3, 4, 5, 6, 7, and 8. So you have 8 vertices. And those are your definitions of a polyhedron. So down here, they give us an example. We have a triangular pyramid over here, or a rectangular pyramid. They want us to find how many vertices they have. There's 5. Remember, it's the corners. So we have vertex D, vertex E, vertex F, vertex G, and then vertex H on top. So that's 1, 2, 3, 4, and 5 vertices. The edges are where two of the faces meet. So those guys are usually line segments. So we have edge DG, edge GF, edge FE, edge DE. So that's 4 right there. Then we have HD, HE, HF, and HG for a total of 8 edges. Then we have the faces. The faces are 1, 2, 3, 4 triangles, and then the base at the bottom is a parallelogram. So that's 1, 2, 3, 4, and then the bottom 5. So we have total 5 faces for this particular pyramid. Here we have another polyhedron. This is a triangular pyramid. I'm not pyramid. Triangular prism. And want to know how many vertices, edges, and faces it has. Remember that the vertices are the corners where the three or more edges meet. So you have R, U, T, S, W, and V. So that's 1, 2, 3, 4, 5, and 6. So you have 6 vertices. Edges, those are the line segments where two faces meet. So you have RU, UV, RV, that's 3 right there. ST, TW, SW, that's 3 right there. Then we have the 6 total right now. So SRS, TU, it's 8, and then WV, that's 9. So I count 9. And then we have faces. Those are, and I see 2 triangles, and I see 1, 2, and 3 rectangles. So we have rectangle SRUT, we have rectangle RVWS, and a rectangle TUVW. Then we have triangle RUV and triangle STW. And those are 1, 2, 5 faces. And there's a equation that we can get called Euler's formula, and it says that the sum of the faces and the vertices is equal to the edges plus 2. So here we have F for the faces, V for the vertices, and is equal to the edges plus 2. So faces plus vertices equals the edges plus 2. So if they give you 2 or more of each, you can find one or the other. So it's a pretty neat actually formula to use. So here we have a hexagonal prism, which is also a polyhedron. They give us that we have 8 faces, 12 vertices, and 18 edges. So if you count these, and if you're not confident in your answer, you can plug it into Euler's formula, and you can check to see if you're correct. So you don't necessarily have to count, or if you do count, you can double check after yourself. So here for number 2A, we have this particular polyhedron. They want to know how many faces it has. So we're given that it has 30 edges and 20 vertices. So again, we can use Euler's formula, which is faces plus the vertices is equal to the edges plus 2. We don't know what the faces are. That's what we're looking for. They give us that we have 20 vertices. We have 30 edges plus 2. So I can subtract 20 from both sides. Faces is equal to 10 plus 2. So we have 12 faces. For example B, they give us that we have 20 faces, and we have 12 vertices, and we're looking for the number of edges. So I have 32, I'm adding 20 and 12. I can subtract 2 from both sides, and I have that the number of edges for that particular polyhedron is 30. This is a pretty neat equation, pretty simple to execute. three-dimensionals into two-dimensional spaces. You can also utilize Euler's formula to turn things into nets. Uh, it's sort of breaking apart the three-dimensional shapes into its two-dimensional counterparts. Um, not too difficult. I'm not really going to spend a lot of time on that. You guys can break up stuff and count the edges yourself. It's just another way of using Euler's formula to verify drawing nets. Okay, cross section. So cross section is the intersection of a solid and a plane. Uh, cross section is going to be in two-dimensional space. So you're cross sectioning a three-dimensional figure and forming two-dimensional shapes with the cross section of that particular shape. So if we look here, we have this polyhedron, which is a triangular prism. We have this yellow plane kind of cutting it. Cross section is sort of like cutting it. And when you have the intersection, the cut forms a two-dimensional shape, and then it's here in red, the red line. The two-dimensional shape is a triangle. So we would say that the cross section that's made when you cut this, that intersection is a triangle. And we have here, down here, a cylinder. And if you look at the cross section, coming down here, here is the cross section in red. It forms a rectangle. So that intersection of this plane and that cylinder would form that particular rectangle. And there's another example of it over here. So we have this particular shape down here. They want to know what the horizontal plane and the vertical plane is. So a vertical plane is a figure that's going to cut from the top to the bottom. So I'm going to try to draw this. Pray for me. So we have a shape up here that looks sort of like this. Alright. I'll draw it again here in blue. Alright, so a horizontal plane is a plane that cuts from here to here. So if I was to draw a horizontal plane, it would cut like this. That's a horizontal plane. And then this intersection over here would form some shape. If we're talking about a vertical plane, it would cut this way. And cut down. So this would be a vertical plane. So when we talk about what type of shape this would have, the shape that it would have for the horizontal plane would be a circle. And the type of shape that it would have when we have a vertical cut here would be a trapezoid. So if I had a horizontal cut here, I would have a circle for my cross section. And down here I have a trapezoid. Not easily seen. Takes a little bit of time to see it. But you would have a vertical, you would have a trapezoid, and then for horizontal, you would have a circle. Okay, so that's section 11-1. The main thing you get out of this is know what vertices, faces, edges are, know Euler's formula, uh, know what a polyhedron is, um, know what a cross section is, and uh, based off the cross section, try to find out how what type of two-dimensional shapes you're going to get from cutting those three-dimensional figures in half. So that's 11-1. 11-2 is going to deal with surface areas of prisms and cylinders. So one particular type of polyhedron is a prism, and a prism is a polyhedron with two congruent parallel faces. Two congruent parallel faces. So I'm going to try and, well, actually, let's just use the picture that they have. Uh, the other faces are called lateral faces. So here is a prism. We have two. We have a pentagonal prism and we have a triangular prism. For something to be a base is a face, right? And we said that a face is basically a shape, whether it be a rectangle, square, triangle, whatever. In the case of the pentagonal prism, since it says the word pentagonal, the name pentagonal is short for pentagon. And if you remember, a pentagon has 5 sides. Pentagon has 5 sides. And the reason why it's called a pentagonal prism is because it has for its base the shape of a pentagon. So what the book just said that the base was? A base is two congruent parallel faces. So if we look at the pentagonal prism, we have a pentagon at the bottom, we have the pentagon at the top. Top and bottom are parallel. Top and bottom are opposites. So these two guys will never touch each other because they're parallel. And these two guys are also identical. So they're congruent and they're parallel and they're the same shape. Since they're congruent, the same shape and parallel, we say that the base is a pentagon. We call it a pentagonal prism. Anything that's not a base, is a lateral face. Anything that's not a base is a lateral face. Lateral just meaning that it's the side of the particular pentagon. So in the case of this prism, in the case of this pentagonal prism, we have 1, 2, 3, 4. We have 5 lateral faces. And these lateral faces are rectangles. For prisms, your lateral faces will always be rectangles of some sort, or some type of quadrilateral of some sort, whether it be a rectangle, whether it be a parallelogram. Always. We also have something called lateral edges, which are just the edges of the lateral faces. Usually the height, and they're usually, most of the time, usually perpendicular to the bases. Here we have a triangular prism to the right. It's called a triangular prism because the base is a triangle. We have 2 triangles. They are congruent and they are parallel. We have a triangle at the top, we have the triangle at the bottom. Since both of the bases are triangles, we call those bases. We have 3 lateral faces. We have one to the left, one to the right, and one facing you to the front. Again, lateral faces tend to be quadrilaterals, whether it be a rectangle, square, or parallelogram, depending if they're oblique or not. We also have lateral edges, is where the two faces meet. This tends to be, we'll find out later, the height of your particular prism, and you need that in order to find the surface area. An altitude of a prism is a perpendicular segment that joins the planes of the bases. The height of a prism is the length of the altitude. The majority, 90%, 99% of the type of prisms that we're going to deal with are going to be right prisms. I repeat, the vast majority of the prisms that we're going to deal with are right prisms. The height for right prisms is the same thing as the altitude. It's going to be a particular segment that connects both of your bases. It's going to be perpendicular. The height is going to be perpendicular to both of your bases. And the height is altitude. Here we have a height here that connects this top base to this bottom base. Here we have a height. The prism is leaned to the side or laying on its side. And the reason why I know this is that both of my shapes, both of these guys are parallel and not touching each other, and they're the same shape. And this guy is perpendicular to both. Notice it has the perpendicular symbol. Another type of prism is an oblique prism, and that's when your prism is sort of leaning towards the side, and in that case your height is going to be outside or inside of your particular prism. This is a rare case. We're not going, or not a rare case. This is a case that we're not going to really deal with in this particular chapter or section. But if otherwise given to you, we're going to assume that all prisms are right prisms. Right prisms, lateral faces are rectangles. Oblique prism is when the lateral faces are non-rectangular. Meaning, if you notice, for the right prisms, these guys are all rectangles. The lateral faces. Here, the lateral faces is not a rectangle, but in this case, it's a parallelogram. So we have a parallelogram for its lateral faces. Then we're dealing with oblique. If your lateral faces are rectangles or squares, then we're dealing with right prisms. And most of the time, we're going to be dealing with right prisms. All right, so one way to get something called the lateral area. The lateral area is the sum of all the areas of the lateral faces. What does that mean? We know that for an area, depending on the shape, but in this case of a rectangle, since most of the lateral surface areas are rectangle, area of a rectangle is length times width or base times height, depending on what you're using. We have 1, 2, 3, 4, right? The sides around the base, 4 lateral areas. So we have this 5, which is perpendicular to all of these guys. So 5 times 4, 5 times 4 in the back, 5 times 3 in the side, 5 times 3, which is the area of those 3 rectangles, 4 rectangles. So in this case of this particular prism, we have 4 lateral faces. If I was to do a net of it, and I think the book already does, these guys would be my lateral faces. 1, 2, 3, 4. We have a base on the top, we have a base on the bottom. So I'll have to just get the area. All of these are 5 because they're all the same. So it'll be 5 times 4 plus 5 times 3 plus 5 times 4 plus 5 times 3. And those would be your lateral area. So it would be 5 times 4 plus 5 times 3 plus 5 times 3 plus 5 times 4. Here's the thing that you can do with this. Your book doesn't really show it algebraically, but if you notice, all of these guys are being multiplied by 5. I can actually factor out the 5 and say it's 5 plus times the sum of 4 and 3 and 3 and 4. And then I can add all of these guys up and say it's 5 times 9 plus 8, or 7 plus 7, which is 17. This 17 is the perimeter of the base. This 17 is the perimeter of the base, and this 5 is your height. It connects the bases to each other perpendicularly. So the lateral surface area, or LA, lateral area, not lateral surface area, I'm sorry. The lateral area is equal to the perimeter of the base times the height. Perimeter of the base times the height. That's your lateral area. When we talk about the area of the bases, if we look down here, we have 4 times 3 on the bottom. We have 4 times 3 on the top. So the area of the bases in this case would be 2 of them, right? 2 times 4 times 3. Since there's 4 times 3, so it'll be 2 times 12, or 24. Since there's 2 bases for a prism, we multiply the area of that base times 2. And that gives us the surface area. So the surface area is equal to the lateral area plus the area of both of the bases, or 2 times the base. And remember that the lateral area is going to be the perimeter of the base times the height. So the perimeter of the base times the height plus 2 times the area of the base. This is our equation for surface area. Here they sort of give you the proof of that using the net, and here is your equation. Lateral area is the perimeter of the base times the height, and if I want to get the surface area, that's the lateral area plus the area of both the bases. So area, just to remind you, is something that's measured in 2 dimensions, so your units are going to be squared. What you're doing basically is you're getting the area of all the faces and you're adding them up together. You're getting the area of all the faces and you're adding them up together, and that gives you the surface area. The lateral area is the area of all the faces that are not the base, not the 2 bases, and you're adding those guys up together, and we call that the lateral area. So I'm going to do, this is a hexagonal prism. Yay, hexagons. We can get the lateral area by multiplying the perimeter base times the height. In this case, the height is 12. It connects both the two hexagons together. The perimeter is going to be 6 times 6 because it's the side is 6, and so it's 6 sides, so 6 times 6, so it's going to be 36 is the perimeter times 12, which gives you 432 meters squared. So that's the lateral area. Surface area, that's going to be doing stuff from chapter 10. It's a regular hexagon. They only give you the side, so we have to find the area. So if you remember, this is a 30, 60, 90. We would have to cut these guys into little triangles to find what it is. So this is a 6. So we have to find the apothem. So if I'm going to blow up that triangle, it's going to be, and this is stuff that we did already in chapter 10. This is going to be this is going to be 30 degrees, which makes this 3, and that's your short leg, which is going to make this your long leg. So remember, your long leg is going to be the short leg times the square root of 3. So in this case, your long leg is your apothem, and your apothem is going to be 3 square root of 3. I think they said they want it in the simplest radical form. So your area of the base is going to be, for this base, it's going to be 1/2 the apothem times the perimeter. So we already have the perimeter of 36, so it's going to be 1/2 3 square root of 3 times 36, which is 54 square root of 3 meters squared. So that's your area of one base. And then the last part they want you to do is find the surface area. So we already have the lateral area, so they want it rounded to the nearest whole number. So surface area is the lateral area plus 2 times the base. We already have the lateral area, it's 432. So it's going to be 432 plus 2 times the area of the base, which is 54 square root of 3. And they want that to the nearest whole number, so it's going to be your answer is going to be 432 plus 187. Which gives me about 619. So 619 meters squared, rounded to the nearest whole number. So that's going to be your answer. This problem puts together all the stuff we've done in the past few chapters, 8, 9, and 10. So those are prisms. Next, we have cylinders. So a cylinder is a solid where the bases are not shapes or shape, but it's not a shape with a side. The bases are circles. So a cylinder is a solid where the bases are circles. Again, the basis has to be the same, and the bases have to be parallel, so congruent and parallel. So that's the difference between a prism and a cylinder. Prism, your bases are shapes such as triangles, rectangles, squares, deca, hecta, octa, nonagon, things like that. Cylinders, your bases are circles. We have right cylinders, just like right prisms, where your height, which connects the two bases, is your altitude. We have oblique, where your height is on the outside. It's not connected to both of the as the shape itself. The definition in the book says that the segment joining the centers are not perpendicular to the planes. Again, we're not going to be dealing with a lot of oblique stuff. It's going to be basically right cylinders. So the surface area of or lateral area of a cylinder is basically the area that is not the two circles. We know that the area of a circle is pi r squared. When we try to get this lateral area of a cylinder, the height is going to be part of it. It connects the two together. So basically, your lateral area of a cylinder is going to be that of a rectangle. We know that the area of a rectangle is base times the length times width, or base times height. In the case of the height is going to be 90 degrees and connects the two. In terms of what the length or the base is going to be, it's going to be the perimeter of the circle. The perimeter of the circle. We know that the perimeter of the circle is the circumference. So it's going to be the circumference of the circle times the height. The circumference of the circle times the height, and that's going to be your lateral area. So when we talk about the surface area of your cylinder, the surface area of a cylinder is equal to the lateral area, which is the circumference. So 2 pi r times the height, or it could be pi times the diameter times the height, plus the area of both the bases, which is 2 times pi r squared. And that's going to be your surface area. Remember that the lateral area is going to be 2 pi r times the height, or it's going to be pi d times the height. Alright, so examples of this, let's say we have a cylinder that has a height of 9 centimeters and a radius of 10. What's the surface area? So remember, surface area is 2 pi r times the height plus 2 times pi r squared. We have a radius of 10. We have a height of 9, so we just plug it in. So 2, and they want the answer in terms of pi. So 2 pi times 9 so say 20 pi plus 9 plus 2 pi r squared. So r squared, that's 100. So 200 pi. So I can add the 200 and the 20, and I can say 220 pi plus 9. And I guess that's what they want. It's going to be centimeters squared. Whoops. I don't know why my brain is not working this morning. 2 pi times 8. So it's going to be 180. My brain's not working today. Sorry. 180 pi. Blech. So 9 times 10 is 90, times 2 is 180. Then I add these two guys together, so it's going to be 380 pi. Centimeter squared. Boom. My bad. Alright, so that's that. Most of these guys, you're just going to essentially fill in the height, radius to solve, or for prisms, you're just going to find the area of the base, multiply it times the height. It's actually pretty straightforward. For this particular problem, they have a stencil roller. They want to know how much one rotation is, so that's basically they just want the lateral area. So in this case, we have a roller with a height of 1.5. In this case, it has a diameter of 2.5. We know that the lateral area of a cylinder is 2 pi r times the height. We have a height of 1.5, and we have a radius of 2.5. They want this rounded to the nearest tenth, so the lateral area is going to be 2 times 1.5 times 2.5 times pi. And I get about 23.6 inches squared. That'll be one row. Alright, so that's section 11.1 and 11.2. Have a great rest of your day, guys.